Hi, welcome to Rangefinding and LIDAR with ON Semiconductor Solutions ecosystem. Why do we need depth data? Depth data allows us to remove ambiguity that may otherwise appear in a standard RGB image. It helps us to distinguish and give meaning to objects within a scene, and this is how depth data enables automation. My name is Adele Cashman. For the next 30 minutes, my colleague Oriol, Theo, and I will talk about LiDAR at ON Semiconductor. First, I'll give an overview of direct time-of-flight LiDAR in the NIR spectrum. I'll discuss the ON Semiconductor LiDAR ecosystem and present some of our SiPM solutions for LiDAR. Later, Oriol will introduce our new direct time-of-flight LiDAR platform system and show a demo using the GUI. Rangefinding or LiDAR, essentially these are saying the same thing. It's a system of measuring depth for surveying, object detection, object avoidance, localization, mapping. And there are other technologies that do something similar, but LiDAR has some particular advantages over other modalities in terms of resolution. While it has been around for a long time, with the advent of the latest technology, we are seeing a rapid growth in LiDAR activity across a really wide range of markets, in particular automotive, IoT, and industrial applications. And that's why this is the focus of our talk today. Why should we be interested in LiDAR for depth sensing? Well, we can configure a LiDAR in many ways. You'll see scanning, flash, single and multi-point LiDARs, all using the same core principles. LiDAR is robust in the presence of weather and having its own light source. It can operate in darkness. Precise and detailed images can be built up by combining multiple point range information. Any solid object can be detected accurately, so there's no ambiguity of depth in an image. And in recent years, with the evolution of the market and of components, we've seen the price of LiDAR systems and components drop dramatically. And this translates to a depth measurement system that's adaptable and widely applicable, bringing high performance and excellent cost-value ratio to a wide variety of applications. There are multiple techniques that can be used for accurate depth sensing, and today we're just going to focus on direct time-of-flight LiDAR using SiPM detector technology. So let me first give a brief overview of this basic concept of direct time-of-flight LiDAR. A light source, such as a laser diode, is used to project a short, narrow pulse of light onto the scene. The light pulse is reflected from a target in the field of view, and the return pulse is detected by the receiver sensor. The time of arrival of the return pulse is accurately time-stamped, and the time difference between the outgoing light pulse and the return light pulse is measured. From this time of flight, we can calculate the distance with a high degree of accuracy. In single shot mode, we would set the threshold of detection high enough to avoid triggering by ambient noise or ambient light. This means we would need a sufficiently high power level in the outgoing pulse so that it would meet our threshold of detection on the return pulse. Bear in mind, the return power will drop with the square of the distance traveled, and the return pulse power will also drop with the reflectivity of the target. So detection can become a challenge for long range and especially for light absorbing targets. In the multi-shot approach, we employ multiple laser pulses for each measurement and then correlate the multiple return timestamps by combining them into a histogram. By combining multiple measurements, the signal-to-noise ratio is enhanced. This technique gives better detection statistics and SNR, and it means we can measure depth with lower threshold of detection and without increasing the laser pulse power. Oriol will demonstrate the histogram technique in practice a little later. An important factor when choosing a LiDAR system design is the laser wavelength. And here we'll take a look at some reasons that might drive this choice of optical wavelength depending on the application. Any wavelength can be used in theory, but in particular, it might be preferred to have a beam that is either visible or invisible in your application. Eye safety will be ensured by design of the emitter. Most importantly, cost of components and component ecosystem are critical considerations, as we need to have both detector and laser to construct the LiDAR. ON Semiconductor SIPMs are manufactured in silicon and are suitable for visible to NIR wavelength detection. Low cost NIR lasers are widely available, and we see in particular that 905 nanometer wavelength has come to dominate the LiDAR market in recent years. At SWIR, or shortwave infrared wavelengths, we see materials have higher cost due to the complexity of manufacturing. Environmental factors such as attenuation in water may be important for an application. So if you needed your LiDAR to operate underwater, a shorter wavelength would be most appropriate. From the spectrum on the left, we see that solar radiation tends to be higher at shorter wavelengths. So this should be considered in particular for outdoor applications. Taking that ASTM solar irradiance model in a little more detail here, we see solar irradiance is plotted on the y-axis. The orange curve is the one of interest here because this is the total irradiance experienced at sea level. If we compare the impact of solar noise on two systems, one a commercially available rangefinder in the visible 635 nanometer wavelength, the second is the ON Semiconductor SIPM direct time of flight rangefinder platform, we see that the solar noise reduces by about a half when we move to the 905 nanometer wavelength. So this SNR can be exploited to improve performance or to achieve the same performance while reducing the required power level at the emitter. The other takeaway from this plot is that a bandpass filter should be used in pretty much all cases to block out all of the ambient light noise that's outside of the wavelength of interest. So the narrower you can make that bandpass filter, the better the SNR on the detector in ambient daylight conditions. A key strategic focus for ON Semiconductor is to offer system, sensor, readout, and laser driver solutions for multiple LiDAR architectures. The diagram on the right here highlights various ON Semiconductor solutions existing in the transmit, receive, beam steering, readout, and power management functions of the LiDAR block diagram. So all of the solutions are highlighted in the colored blocks. Later, we will present actual implementation of this block diagram in a real LiDAR system. Sensile Division and ON Semiconductor have developed a series of proof of concept demonstrator platforms. Today, we're making available reference designs to assist with customer LiDAR developments, and we've also launched a LiDAR Partners program through which our customers can benefit from collaboration with ecosystem partners, and you'll find that on our website. Here's a brief primer on SiPM and SPAD operation. The SiPM is formed of an array of closely packed single photon avalanche diode or SPAD sensors. The SiPM operates in Geiger mode, that is above the breakdown voltage, where a detected photon triggers an avalanche of charge carriers in the SPAD. The high gain of the SPAD due to the avalanche process produces a measurable pulse of current when a photon is detected. The integrated quench resistor in each SPAD quenches the avalanche to reset that SPAD following a detection event so that it's ready to detect another photon after a few nanoseconds. Thus, each SPAD or microcell is capable of detecting a single photon and operates independently. The SiPM can be used to precisely measure photon arrival time, and with its pseudo-analog construction, the SiPM signal also provides a measure of intensity of light. The photocurrent of the SiPM will be proportional to the number of photons detected. ON Semiconductor SIPMs also benefit from the unique fast output, which enables high count rates. Why use SiPM for LiDAR rather than another photodiode? So PIN diodes have been around for a long time and do a good job of detecting photons. However, the low gain of the PIN diode means that it is not a suitable detector for long range, where the return signal power level is low, since the photocurrent signal can't be detected at low optical flux. APDs have higher gain of between 100 and 1000, and they also operate in linear mode. And APDs have been used in LiDAR, but we do see APDs gradually being displaced. A key drawback of the APD is lack of uniformity between devices. Also, for linear mode operation, APDs require a very high bias voltage. Both of these factors can translate to a more complex and expensive LiDAR product. SPADs, on the other hand, allow single photon sensitivity, so even the faintest reflections from objects can be detected. In Geiger mode operation, the SPAD has a gain of about 10 to the 6, and this means that a single photon produces a measurable photocurrent, enabling ranging at long distance. SiPMs are built on the same technology as the SPAD, but in the SiPM, all SPADs are summed together in parallel, enabling detection of either single or multiple photons in a compact sensor. And SiPMs and SPADs both benefit from low voltage operation and excellent uniformity, as well as high gain. We can also build arrays of both SiPMs and SPADs. So it's not surprising that SiPMs and SPADs are fast becoming the detector of choice for many LiDAR applications. At ON Semiconductor, we have the very well-established C-series family of sensors, which may be used for LiDAR with visible wavelengths. And in recent years, we've led the market with NIR sensitive R series family of detectors, from RA through to RDM. We've seen improved performance to meet demand for increased PDE to enable longer range LiDAR system development. We expect this trend to continue as we develop new detectors with higher PDE and lower noise. And today's focus will be on the RB series family, which is suitable for short to mid-range applications in IoT, industrial, and robotics. RB series sensors have been developed specifically with the LiDAR application in mind. The high sensitivity at 905 nanometers allows detection of very low NIR signal levels. Single photon sensitivity of the SiPM can be exploited in conjunction with multi-shot histogramming to detect return signals close to the noise floor with a high degree of confidence. The low operating voltage makes application straightforward, and ON Semiconductor has a lot of materials available to assist customers in design and biasing and readout circuitry. Thanks to the CMOS process, the SiPM provides a very uniform performance characteristic, again simplifying product design. SiPMs inherently have high bandwidth due to the Geiger mode of operation, and this is very useful in LiDAR. The sub 1 nanosecond rise time minimizes jitter on the time of flight timestamp measurement. And furthermore, ON's unique fast output with a 2 nanosecond pulse width allows for detection at higher count rates, which is beneficial for LiDAR. For example, when we're detecting returns from multiple objects that are close together in a scene. The SiPM comes in a robust, clear molded lead frame package and can be operated up to 85 degrees Celsius. This family of sensors comes in several variants. So you have a choice of 10 micron, 20 micron, and 35 micron microcell size, which means it's possible to trade off PDE and dynamic range to suit the application-specific requirements. And we have evaluation boards available. Summarizing here, the benefits of ON Semiconductor SiPMs for LiDAR. The SiPM is a high-performance, single-photon sensitive sensor. with high gain and high detection efficiency, low noise and fast timing, making it ideally suited for LiDAR applications. ON Semiconductor has developed a family of SiPM devices that make use of these features to provide cost-optimized solutions with market-leading reliability. And our R-series range of sensors are specifically designed for use in NIR LIDAR with lasers in the 850 nanometer to 905 nanometer range. Thanks for listening. I'll be available for questions later, and I'll hand it over to Oreo here.
Thank you very much, Edel, for the interesting overview on LiDAR and on the ON Semiconductor ecosystem for this application and our leading silicon photomultipliers. In this second part of the session, we'll discover an actual range-finding system based on technologies and products for LiDAR. For a start, I would like to refresh the concept that Edel introduced of the major functions in LiDAR systems. This is very relevant because ON brings value to almost all the critical areas for the application, with our leading silicon photomultiplier technologies and a comprehensive portfolio. More importantly, our expertise in integrating all these technologies makes a difference to speed up new LiDAR development. And this is actually what we are introducing today: the Silicon Photomultiplier Direct Time-of-Flight LiDAR Platform, an example for developers of how to bring together all our technologies in a reliable, compact, and cost-optimized LiDAR system. Not only that, this is a tool to evaluate our technologies for different use cases out of the box, just needing to connect the USB cable to your laptop and launch an easy-to-use graphical user interface. No need of installation. A development kit targeting single-point range-finding applications, with an operating range between 10 centimeters and 23 meters, and Class 1 laser certified, so it is intrinsically eye-safe. It clearly reaps the benefits of our RB series silicon photomultipliers, decreasing the complete system cost and making it ready for mass deployment. The Direct Time-of-Flight platform is targeting industrial and IoT applications with a special focus on single-point range-finding, but not exclusively. Distance and position measurement, as well as object detection, would be the enabling baseline capabilities, which then spawn into a myriad of use cases: crops monitoring, building information modeling, field level monitoring, people occupancy monitoring, and more. Our field teams can help you understand the best way to adapt our rangefinder platform into your particular application. Now that we understand the purpose, let's dive deeper into the system blocks and how the application is realized. 6 main areas are clearly identified, which again trace back to the LiDAR block functions seen earlier. The transmitting block, which encompasses the 905 nanometer laser LED and driving circuitry. The receiving system with the RB silicon photomultiplier diode together with the necessary readout devices, including amplifiers and discriminators. At the core of the application, the FPGA, which handles the direct time to digital conversion of the pulses, the control for all the power management systems, as well as the communications via the serial UART interface used for the GUI. One question that you are probably asking yourself at this point is, what are all the actual components under these blocks enabling the application? Here comes the answer. Our silicon photomultipliers and all the surrounding systems for power management, laser driving, and reading out come together. ON Semiconductor leading and comprehensive portfolio for LiDAR applications brings value to the customer at the system level, where you're looking for optimization, integration, and reliability. We're happy to share all this unique system know-how to help you fulfill your application while speeding up the development. What other benefits does Rangefinder platform offer for you? Well, in first place, the graphical user interface functionalities. Let me show you how. First of all, once the GUI is launched, we connect the USB cable and the right port will pop up as first in the drop-down tab. Then we press connect and the GUI will start up. You'll notice in the TDC cal section that the system automatically calibrates the time to digital conversion every time the rangefinder kit is connected. To ensure accurate and precise measurements under all conditions, the system calibrates the delay of FPGA gates at the given point in time. It is possible to calibrate the system at any time with the software reset button, and it is recommended to do so often when performing measurements during some minutes. Before measuring, the supply voltage to the laser diode needs to be enabled. This is a fixed voltage and not adjustable. Secondly, the bias voltage of the silicon photomultiplier needs to be enabled as well. In this case, the voltage biasing of the sensor is adjustable from -45 volts to -32 volts to adapt to different use cases of different light conditions. High ambient light environments, like outdoors, will require lower absolute bias levels. If the maximum current value for the silicon photomultiplier diode is exceeded, an overload warning is triggered. In such cases, the bias voltage needs to be reduced either with a slider or by pressing outdoor to automatically set the voltage to -35 volts until the overload warning disappears. Finally, before starting to perform measurements, the laser pulse width needs to be enabled. The parameter is not adjustable and fixed to 18 nanoseconds internally to fulfill the eye safety requirements for Class 1 lasers. The value 10 is a dimensionless internal system variable that corresponds to this pulse width. Now we are ready to begin measurements, and this starts with the trigger. The results will be displayed on the histogram, number of samples compared to distance. The actual number of samples can be adjusted up to 254 with the slider. Next to this histogram chart, the average distance as well as the maximum values are numerically displayed. The histogram results can be visualized as time values or distance values. Beyond the trigger mode, the rangefinder operates as well in continuous mode. Once you set the number of samples slider to the max higher edge. The run button now indicates that we are in the continuous mode. In this mode, the number of samples per measurement can be set to different discrete values in the buffer length section, from 100 up to 10,000. Repeated measurements with the selected number of samples will be performed. The tool allows to save the measured data in dToF files, both in the trigger and continuous modes. For that, the Auto Saves checkbox needs to be selected, and you can set a specific directory for the exported files, as well as a name, for example, test01. In continuous mode, you can limit the number of measurements saved, same as number of dToF files generated, with start and stop input text boxes. All the saved dToF data files can be loaded into the chart for comparison. That's it actually. Better images than words. Out-of-the-box operation, adjustable sensor bias voltages, save and load data, and others. In essence, a fast system and product evaluation. And what else do we have? The optic and lenses system is optimized to maximize distance measurement and achieve the highest sensitivity in the operating spectrum. The system is Class 1 FDA certified, thus working at low power and being eye safe. The time to digital conversion is handled by the FPGA as learned, and two different supplying modes are supported for convenience. The kit includes the USB cable. All our expertise and customer education approach on how to integrate and optimize our silicon photomultipliers for LiDAR applications materializes in available collaterals, papers, and design guides, a unique support in the market. The development tools and kits you've just seen are another example of tools to help you speed up your development cycles. All the collateral and manufacturing files are available. Beyond that, our LiDAR simulation models under request that allow to accurately anticipate the performance of the silicon photomultipliers in different conditions before developing any hardware. Available here as well the list of our silicon photomultipliers families. This brings us to the end of this session. We hope you have a better understanding now of ON Semiconductor LiDAR unique ecosystem and all the benefits it brings. Three main pillars underpin our value proposition. On one side, excellent system solution expertise, fostered by our extensive portfolio that covers most of the key functions in the application and by the deep know-how on how to bring these parts together to an optimal system. On the other side, multiple development tools, hardware and software, and educational resources that will help you iterate faster and reduce the development cycles and the time to market for new products. Lastly, at the core of the ecosystem, our silicon photomultiplier leading technology, superior or best in class for all relevant parameters, photo detection efficiency at 905 nanometer wavelength, highest fast output capability, excellent bias voltage temperature stability, and many others as we have seen. This technology lead is a value advantage for our customers, not only for the direct benefits of higher quality outcomes, but equally or even more important because it brings down the system complexity and cost while increasing reliability. When working on LiDAR, ON Semiconductor is your value-added partner. Reach out to us and start taking advantage of our ecosystem. Thank you very much.